So second one, computing static forces. Okay, so I'm just going to draw a generic figure. Let's say that this is pinned, this somebody. There are forces, and then because there are forces on this, it's going to start spinning. And so what we want this to happen is we want to connect this pin joint to a motor, and that motor should apply a torque which will prevent this body from rotating. So there is a torque needed to prevent this from moving. So here the problem is, given F1, F2, and so on, compute the motor torque needed to keep the body from rotating, which is the same as saying, how do you keep this in static equilibrium? Yeah, I'll show you. It's a short derivation, doesn't take too much time, but I think you'll appreciate how it comes from. How do you really get the Jacobian here? There's something called principle of virtual work, which it might have been taught in when you did bending of beams, perhaps, where you really apply virtual forces, and those forces called the force is called. So there are forces in a beam which keeps it in equilibrium, but those forces lead to a virtual displacement, not real displacement. And then you find what is the effect of work done by that displacement, and you sum that up, and then all that should be equal to 0 because actually the beam is not doing any work. So it's similar to that. So virtual work. So what we'll do is we'll assume that these forces F1, F2, and so on produce movement or motion of the body in some way. So that can be written as F transpose dr. So how did I get this? Well, what's the work done? It's force times displacement, right? So force, I've written that down. Dr is the displacement. So the dot product gives me the work done. Okay, so dr is the displacement. That is a virtual displacement. It's not real, and eventually it'll not even appear in the equations. The reason why I wrote F transpose dr is because when we write any vector here, we're going to assume it's n cross whatever 1, right? So it's 2 cross 1. 2 cross 1 because we're looking at planar motion. You can move in the xy direction. And this force is also 2 cross 1 because it is it's a vector, right? You can have fx, fy. What F transpose does, it converts that into 1 cross 2. And so when you take the product here, you get 1 cross 1. And you know that work is a scalar. It's a number. It's not a vector, right? So it all works out. Now that's the work done due to the virtual displacement in the horizontal and vertical direction. But we also have a motor which is applying a torque tau, and that torque will produce a virtual rotation by d theta. So torque creates a virtual displacement d theta. So this is virtual rotation. Now, in this case, for a two-dimensional example, the rotation is a number, right? It's not a vector. So 1 cross 1. And torque, I kept it as torque tau raised to transpose because just to be true to the way we've defined it. If it's a vector, it's going to be n cross 1. So I need to do 1 cross n. So in one dimension, or say 2 dimension, it really doesn't matter. But when you go to 3 dimensions, it's important to keep tau transpose in the circuit. So now we have work done by a virtual displacement dr. We have work done by the torque. And remember that if there is work done by two things, the net should be the same. I mean, they should balance out. If they don't balance out, there'll be net rotation of this. So equating these works together, we can write d theta is f transpose dr divided by d theta. So we have tau transpose equals f transpose dr d theta. But what you notice is that the partial derivative, I know it's a delta, but it's really the partial derivative of r with respect to theta is nothing but the Jacobian. Okay, and then because we don't like the transpose appearing the way it is, so we take transpose of both sides of both sides, and we end up with, so the transpose of transpose is the vector itself, so that'll be tau, and then we write f transpose j transpose. This is the same as j transpose f, right? The rule is that AB transpose is B transpose A transpose. That's a fact. So I'm using that. So I exchange F transpose J, so it's going J transpose F. And then when I take the transpose of F, it'll be 2 times, it'll be F. So this is the formula I was after. The torque is J transpose F. Okay, so this is kind of interesting is that when you did this calculations in statics class, you probably found a moment arm, right? If you had, let's say, something as simple as this, there's a force, and then you need to find what torque you need to apply so that you have this pendulum in equilibrium. You need to find the moment arm and then compute the relation between tau and f by drawing a free body diagram. It turns out you get the same answer if you use this formula, J transpose f. You just need to find the Jacobian of this point, and you're done. You don't need to draw any free body diagram. Okay, so we'll see how to apply this on the same two-link pendulum. Okay, clearly, if you don't do anything with the motors, then this pendulum is going to move around, right, and eventually come to rest in a vertical position. But we want to just hold it onto this position. So how do you do that? Okay, so obviously we assume that theta 1 is not equal to theta 2 is not equal to 0. So it has to be in some non-zero position. Now, this kind of a problem, you can totally solve it without using Jacobian. You could just draw a free body diagram from your statics class for the two links, find what torque is needed at joint 1, torque 1, and then draw a free body diagram the second link, and then do force equilibrium, compute the torque 2, and then you're done. Okay, I'm going to show you an alternate way which does not need free body diagrams. Okay, so just write the formula which we derived. It's torque is summation J transpose F. So we need to sum all the forces. It's a J transpose F sum, right? So What are the torques? Well, there is a tau 1, there's a tau 2. And then if we see forces, well, there are two forces here. One is due to m1g, other one is to m2g. So the Jacobian, I'll write the Jacobian of G1. Okay, so G1. And then we need to write the corresponding force. And this force should be in the world frame because the Jacobian is going to be in the world frame. So the force is acting in the vertically downward direction. There'll be an x component and the y component. The x component is 0. The y component is m1g, but since it acts downward and our convention is positive is upwards, this is going to be minus m1g. So you can see it here. This is positive, right? So it's downward. So that's a transpose. And then J G2 transpose 0 minus M2G. So if you know JG1, JG2, just one line, you can get the answer. No free body diagram needed. Okay, so we had derived an equation for JG1 and JG2 in the last class when we talked about velocity. So we'll just reuse that. Okay, so what's JG1, JG2? We had it over here, I think. So JG1 was this. Sorry. This was right here. And then JG2 here was this whole thing. So we can reuse that. Let's use that. Okay, so I'm going to expand this out, right, in terms of the formulas for JG1, JG2. Okay, so tau 1, tau 2 equals, so here's JG1. Okay, so first of all, there's JG1 is, just go here. So this is JG1, but what I'm interested in is JG1 transpose. So I need to take the transpose of that. So C1 cosine theta, this will go up, right? And this 0, 0 will come in row number 2. So let me write it that way. C1 cosine theta 1, C1 sine theta 1, 0, 0. JG1 transpose, and then 0 minus M1G plus, so the three dots means it's continued on the new line. And then we have JG2, which I need to take and then take the transpose. So it was something like this: cosine theta 1 plus theta 2 plus L cosine theta 1 C2 sine theta 1 plus theta 2 sine theta 1 C2 cosine theta 1 plus theta 2 C2 sine theta 1 plus theta 2, and then 0 minus 2G. Okay, so last step is an exercise in simplifying this. The good thing is there's a 0 there, so it's much easier to write that formula than it normally would be. So when you basically do the matrix multiplication, you get a 2 cross 1 matrix or vector, sorry, M1G C1 sine theta 1 into g sine theta 1 plus theta 2 minus m2g L sine theta 1, then minus m2g c2 c2 sine theta 1 plus 2. You can actually check some of these, right? So we had pendulum like this. This is theta 1, and then this was theta 2, but then this total angle is theta 1 plus theta 2. M2G. Tau 2. I'm just going to check tau 2. So tau 2, to compute tau 2, what you need to do is you need to do a force equilibrium or a moment equilibrium about this point. Let's call that, I think we called it P. Okay, so moment at P should be 0. So we can see it's M2G. That's the force downwards times the moment arm. So the moment arm would be the distance from here to here. So this distance is C2. So it's going to be C2 sine theta 1 plus theta 2. So that goes in here. So check this and check this. Okay, now there's a negative sign because a convention is always clockwise is negative. So how do you see that? Well, if you saw the way I set the axis, x0, y0. Okay, so where is z0? So to find compute z0, you can use the right hand rule, or the simpler way I like to do is take your right hand, curl your fingers from x0 to y0. So when you do that, your thumb gives the direction of the z-axis. So the z-axis points out of plane. So it's sticking out, right? So that is the positive direction. Now, what is the effect of M2G? It's going to make these things, the torque produced by M2G is going to be clockwise. So clockwise, what's the sign of clockwise rotation? Well, you do the same thing. You take your right hand, curl your fingers along this arrow. When you do that, you see that your thumb points inside the plane of the paper, which means that this torque is negative because it's clockwise. So clockwise is negative, counterclockwise is positive. So here M2G is clockwise. Turn it clockwise, thumb gives you the negative direction. Okay, do it with the right hand, don't do it with the left hand. So that checks out, right? You could also do the same thing for this joint. All you have to do is you'll have to consider the effect of M2G and M1G, and then take the force, the force downwards, take the moment arm from this point O, and then you'll have two things. One is contribution due to M1G, contribution to M2G. Sum them up, and you'll see that this is the contribution to M2G, and this was the contribution due to M1G. Okay, so here is a method which does not involve free body diagrams. It's a good method because it's really hard to automate a free body diagram using computer code, right? It's much easier to automate computation of Jacobians. And that's where we're getting to. I'll show you how to derive the equations of motion of a two-link pendulum. So you might have done a single link pendulum, one link pendulum, maybe in high school, and it was easy to compute that by hand. I'll show you that the equation for double pendulum will run into pages, and you just can't do that by hand. And we'll use a symbolic package to do it. Thanks to this thing, which is the Jacobian, we'll actually be able to write it down in a very short form and it'll translate. So we'll do that in a couple of classes.